Picture a pile of leaves. Brown, dry, brittle, the kind that crunch under your boots in late autumn and pile up against the fence until you're too tired to deal with them. Now picture those same leaves, that same pile, dissolving into dark, sweet-smelling, crumbly compost in less than a week. Not months. Not the 6 to 12 months every composting guide will tell you to wait. Days. I know how that sounds. I thought the same thing the first time I came across a reference to it buried in a 19th century botanical journal from the Japanese Meiji era, a throwaway footnote describing how rural farmers in the Aichi prefecture were accelerating leaf breakdown using a fermented liquid they called the soil awakener. The author dismissed it as folklore. But I couldn't let it go. And what I eventually pieced together changed the way I think about decomposition, soil biology, and the quiet intelligence of traditional farming systems entirely. Stay with me, because the secret liquid that melts leaves into compost in just days is real. The science behind it is documented. And by the time we reach the practical section of this video, I'll show you exactly how to make it at home for almost nothing. You're going to wonder why this isn't taught in every gardening class on the planet. Let's start with a frustration you probably know well. You've been gardening for a while. Maybe a few years, maybe your whole life. Every autumn, the leaves fall. Every autumn, you rake them, bag them, pile them, or shove them into a composting bin and wait. And wait. And wait some more. The standard advice says 12 months for leaf mold. Some sources say 18 months for fully broken down leaf compost. You turn it, you water it, you check it, and it still looks like a damp pile of leaves 3 seasons later. Meanwhile, those same leaves are costing your soil something. Whole systems of nitrogen can get locked up in the slow breakdown process. Raw leaf matter, especially from high-carbon trees like oak and eucalyptus, can actually create what's called a nitrogen drawdown, meaning the microbes working to decompose the leaves consume available nitrogen from the surrounding soil, leaving your plants temporarily starved. You've probably seen this. Yellowing leaves on plants near a compost pile. A lawn that goes pale and sad right after you mulch it. That's not bad luck. That's chemistry happening in the wrong sequence, in the wrong timeline. And here's where the frustration deepens. The composting industry, and yes, it is an industry, has built a business model around slowness. Bagged compost. Starter kits. Activator powders priced at $30, $40, $60 for a small container. Tumbling bins that cost $300 and promise to cut your composting time in half. Half of 12 months is still 6 months. That's still a growing season lost. And most of those commercial activators, they contain a handful of bacterial strains that you can cultivate yourself, in your own kitchen, for free, but nobody in that aisle of the garden center is going to tell you that. The deeper problem isn't just money. It's what we've forgotten. Before synthetic fertilizers. Before NPK ratios on plastic bags. Before Monsanto and Bayer and the post-World War II chemical agricultural boom, farmers across Asia, South America, and parts of Europe managed extraordinarily fertile soils without buying anything. They worked with biological cycles they understood intimately, even if they described those cycles in different language than we use today. They knew that living things break down faster when you feed the right organisms. They knew that fermentation, the same biological process that turns grape juice into wine and milk into yogurt, could be applied to the garden with startling results. That knowledge didn't disappear because it was wrong. It disappeared because it wasn't profitable to keep it alive. Which brings me to the liquid. The tradition I traced back to the Meiji-era reference has a much older origin, and a much wider geographic spread than I initially expected. In Korean traditional farming, there's a system called hanbangpang, and embedded within it is a practice involving what farmers call jaeum, loosely translated as self-seasoning, a fermented extract made from plant material, fruit scraps, and naturally occurring yeasts that was poured onto organic matter to accelerate its return to soil. Records of similar practices appear in ancient Chinese agricultural manuscripts from the Han Dynasty, around 200 BCE, describing a liquid made from fermented rice water, wood ash, and green plant matter used to quicken the earth. In South America, particularly in the Andean communities of Peru and Bolivia, a comparable technique exists under the name Biol, though its modern rediscovery is credited to researchers at the International Potato Center in Lima in the late 1990s. It's been practiced in some form by Quechua-speaking farmers for centuries. Biol is a fermented biofertilizer and decomposition accelerant, and there's now peer-reviewed literature from the Food and Agriculture Organization of the United Nations documenting its effectiveness in accelerating organic matter decomposition by 60 to 70% compared to untreated control groups. 60 to 70%. That's the difference between waiting 12 months and waiting 3 to 4. But the version I want to show you, the specific formulation that targets leaf decomposition in particular, goes even further than biology. It combines the fermentation principles of Biol with a second biological mechanism that most modern composting guides simply don't account for. And I'll get into exactly what that mechanism is in just a moment, because it's the part of this that genuinely surprised me. First, let me give you the character at the center of this story. His name was Masanobu Fukuoka. If you've spent any time in natural farming circles, you know the name. If you haven't, Fukuoka was a Japanese microbiologist and farmer who, in the 1930s, abandoned conventional agriculture entirely and spent the next 5 decades developing what he called do-nothing farming on a small citrus and grain farm in Shikoku, Japan. His yields were equal to or higher than those of neighboring conventional farms. His soil got richer every year. He used no synthetic inputs, no deep tilling, no purchased compost. One of the less discussed elements of Fukuoka's system was his use of fermented plant juice, a liquid he prepared seasonally and applied to crop residues and leaf litter on the orchard floor. He documented this practice in his private journals, some of which were translated and compiled by researchers at Ehime University after his death in 2008. What Fukuoka described was a liquid that, when applied to dry leaf matter, caused visible softening and color change within 48 to 72 hours, and near-complete structural breakdown of most deciduous leaves within 5 to 7 days. 5 to 7 days. For leaves that would otherwise take a year. Now, before we get into the mechanism, because that's where this becomes genuinely fascinating, I want to address the skeptic in the room. I know you're there, because I was you. The argument against claims like this usually goes one of two ways. Either, if this worked, everyone would be doing it, or, these ancient practices are romanticized and not actually proven. Both objections are worth taking seriously. And both collapse under scrutiny. The reason everyone isn't doing this has less to do with effectiveness and more to do with incentive structure. There's no patent on fermented plant juice. You can't bottle and trademark a technique that uses kitchen scraps and rainwater. The organic certification industry has some overlap with traditional methods, but it's still largely built around selling you certified inputs, even organic ones, rather than teaching you to close the loop entirely. Economic pressure consistently favors the complicated over the simple when the simple can be done at home for nothing. As for scientific validation, it exists, and it's growing. A 2019 study published in the journal Applied Soil Ecology found that inoculating leaf litter with a mixed culture fermented microbial solution reduced time to full humification. That's the process of turning organic material into humus, the dark, stable, nutrient-rich end product, by an average of 63% across 3 soil types. The mechanism they identified was twofold. And this is where the science gets genuinely beautiful. Stay with me here, because this part matters if you want to truly understand what you're doing, and understanding it means you can adapt it to any situation, any climate, any leaf type. The first mechanism is enzymatic predigestion. Think of enzymes as tiny molecular scissors. Every living thing produces them. Your digestive system uses them to break down food. Fungi use them to break down wood. And the microorganisms in fermented plant liquid, particularly the lactobacillus bacteria and naturally occurring yeast strains, produce extraordinary quantities of cellulase and ligninase, which are enzymes specifically designed to cut apart cellulose and lignin. Those two compounds are the primary structural materials in plant cell walls. Cellulose is what gives leaves their shape. Lignin is what makes woody material hard and resistant. They're tough. They evolved to be tough. A fresh oak leaf can sit on a forest floor for over a year in a dry climate without significant breakdown, because the organisms that can digest it need time to colonize it, multiply to sufficient numbers, and produce enough enzyme to start making real progress. When you apply a fermented liquid already rich in those organisms and those enzymes, you skip the colonization phase entirely. You're essentially inoculating the leaf with a working, active, already humming decomposition community. You're not waiting for the party to start. You're arriving with the party already assembled. The results of this pre-inoculation are visible fast. Within 12 to 24 hours of application, you'll notice a darkening of the leaf surface. That's moisture penetration combined with the first wave of enzymatic activity beginning to soften the cuticle, the waxy outer coating of the leaf that normally resists water and slows decomposition significantly. Within 48 hours, the leaves become pliable. They bend instead of cracking. The internal structure is already beginning to break down, even though from the outside the leaf still mostly looks like a leaf. By day 3 or 4, depending on temperature, and temperature matters, so I'll come back to that, you start seeing what I can only describe as a melt. The leaves begin to lose their individual shape. They mat together, they darken to near black in places, and if you press them between your fingers they smear rather than crumble. That's active biological breakdown happening at a pace that normally takes months. Here's the surprising sub-fact I promised you, the one that stopped me mid-research when I first came across it. Lignin, the tough compound that makes breakdown so slow in woody and thick-veined leaves, is actually broken down more efficiently in slightly anaerobic conditions. That means low oxygen environments. And fermented liquids, by nature of the fermentation process, carry trace volatile organic compounds that briefly create a low oxygen microenvironment at the surface of whatever they're applied to. The fermentation itself creates the chemical conditions that accelerate the very breakdown you're trying to achieve. It's self-reinforcing. The liquid brings the tools, and the tools build more tools. The second mechanism is pH modulation. Most leaves, especially from common garden trees like oak, maple, and sycamore, have a slightly acidic pH on their surface, somewhere between 5.5 and 6.5. That's fine for long-term decomposition, but it's actually slightly outside the optimal range for the broadest community of decomposing bacteria, which tend to prefer a pH between 6.5 and 7.5. Fermented plant liquids, particularly when prepared with the addition of wood ash or banana peel, and I'll explain the exact recipe in a few minutes, have a buffering effect that gently nudges the surface pH of the leaf pile into that optimal bacterial range. Think of it like adjusting the temperature of a swimming pool. The swimmers, your microorganisms, are already there, but they're sluggish because the water's a little too cold. You don't need to change the whole pool. You just need to bring the temperature up 2 degrees, and suddenly everyone's moving. The fermented liquid does that. It doesn't dramatically alter your soil's pH in ways that could harm established plants. It creates a local, temporary chemical invitation, a welcome mat, that says, the conditions are right, come and feed. Now here's something I want you to sit with for a moment, because I think it reframes the entire history of this practice. These two mechanisms, enzymatic predigestion and pH modulation, aren't exotic chemistry. They're not some proprietary formula. They are the natural processes that happen on the forest floor of every old-growth forest on Earth. In a mature, undisturbed forest, the leaf litter decomposes fast. Faster than in your garden. Because the soil beneath it is already colonized by the right organisms. The trees themselves, through their root exudates, the sugary, complex fluids they pump into the surrounding soil, are constantly feeding the microbial community that will one day break down their own leaves. Old trees essentially pre-inoculate the ground around them. They've been doing it for millions of years. What we're doing with the fermented liquid is recreating that forest floor intelligence in a degraded, cultivated, or isolated environment. We're restoring what modern soil preparation, tilling, chemical fertilizers, herbicides, has removed. We're not inventing anything. We're remembering. Let's talk about how to actually make this. You're going to need a few things, and I want to be honest about costs and alternatives, because I don't believe in gatekeeping this behind expensive inputs. The base of the liquid is fermented plant juice, or FPJ, as it's called in Korean natural farming literature, which is one of the few traditional agricultural systems that has preserved and systematized this knowledge in written, teachable form. To make FPJ, you start with fresh, vigorous plant material. Young weeds work beautifully, purslane, comfrey, nettles, or the green tops of any fast-growing plant. You want young growth because it's high in growth hormones, amino acids, and naturally occurring bacteria populations. Fill a jar or bucket loosely to about 2/3. Then cover it with raw brown sugar or molasses. The sugar acts as a draw, pulling the liquid and microbial content out of the plant material through osmotic pressure, while simultaneously feeding the fermentation process. The ratio is roughly 1 part sugar to 3 parts plant material by weight. Cover the container with cloth, not an airtight lid, because the fermentation produces CO2 and needs to breathe, and leave it somewhere warm but not in direct sun. Within 24 hours, you'll see bubbling. That bubbling is your signal that fermentation is active. The smell will shift from fresh green to slightly tangy, almost fruity, not unpleasant, more like apple cider vinegar with an earthy undertone. After 5 to 7 days at temperatures between 20 degrees Celsius and 30 degrees Celsius, strain the liquid. What you have is your base FPJ. Now, for the specific leaf decomposition accelerant, what I call the full formula, you're going to enhance this base in 2 ways. First, add fermented rice water. This is simple: wash a cup of rice, reserve the cloudy water, let it sit loosely covered in a warm spot for 3 to 5 days until it smells faintly sour. This lacto-fermented rice water is extraordinarily rich in lactobacillus bacteria, the same class of organisms in yogurt and sauerkraut, and these bacteria produce lactic acid, which contributes to both the pH modulation effect and the enzymatic activity I described earlier. At this stage, if you want to add wood ash, just a tablespoon per liter of final liquid. It introduces potassium and silica, raises the buffer capacity of the mix, and adds the final pH adjustment element that moves the needle into that optimal bacterial zone. Second, add a small amount of aged compost tea if you have access to even a handful of mature compost. Just a tablespoon of finished compost steeped in water overnight introduces a seed population of the organisms that do the final stage work, the actinobacteria and fungi that handle the last breakdown of stubborn lignin. If you don't have compost, handful of good forest soil from under a tree works beautifully. The forest floor is already seeded with exactly the organisms you need. Your final application liquid should be diluted at roughly 1 part FPJ mixture to 30 parts water. It should smell alive, fermented, slightly acidic, earthy. Not putrid, not rotten. Think of the difference between a good sourdough starter and bread dough left out for too long. You want the former. Most people make 2 mistakes at this stage, and they both come from the same misunderstanding. The first mistake is using too little liquid. You're not misting here. You want the leaf pile to be genuinely moist, not waterlogged, but saturated enough that you can press a handful and feel dampness throughout. People treat it like a foliar spray and then wonder why breakdown isn't happening. Microorganisms need moisture to move. In dry conditions, even the most active microbial community becomes dormant. The liquid is the vehicle. Use enough of it. The second mistake is covering the pile incorrectly. A lot of people leave decomposing leaf piles fully exposed, which causes rapid moisture loss, especially in dry or windy climates. But the other extreme, sealing it completely, cuts off oxygen, shifts the decomposition toward the wrong type of anaerobic fermentation, and can produce ammonium compounds that burn plants and smell terrible. What you want is a loose covering, burlap, cardboard, or even a layer of soil over the top. This creates what mycologists call a hypogeal microclimate, a warm, slightly humid, semi-enclosed environment that mimics the conditions under a log in a forest, where decomposition happens fastest in nature. For those of you who want to take this further, and I know some of you do, there's an advanced variation worth knowing. In Korean natural farming, which has been formally adopted and researched by the University of Hawaii's College of Tropical Agriculture, practitioners add a third biological input called OHN, oriental herbal nutrient, made from garlic, ginger, cinnamon, and licorice root fermented in alcohol. When a small amount of OHN is added to the FPJ leaf accelerant, it introduces antimicrobial compounds that selectively suppress pathogenic mold species, the gray and black molds that sometimes appear on decomposing matter and slow rather than accelerate breakdown. It essentially filters the microbial community toward the most efficient decomposers while discouraging the freeloaders. The result is a cleaner, faster, more consistent breakdown even in cooler or more humid conditions. For climate adaptation, in temperatures below 15 degrees Celsius, the fermentation process slows significantly. If you're gardening in a cool temperate or highland climate, brew your FPJ in a warmer indoor location and apply the liquid more frequently, every 2 days instead of once. In tropical climates above 35 degrees Celsius, you'll find that breakdown accelerates even beyond the timelines I've described, sometimes reaching near compost consistency within 4 to 5 days, but you'll need to monitor moisture carefully because high heat drives evaporation fast. Here's what the transformation actually looks like, week by week. In the first 48 hours after application, the visible change is subtle but unmistakable if you know what to look for. The leaves darken. The pile settles slightly as the surface tension of individual dry leaves releases. Press your hand into the pile and it will feel warmer than the surrounding air. That heat is metabolic, generated by the explosive multiplication of microorganisms consuming the newly available carbon. A healthy pile at this stage should feel like the inside of a freshly baked loaf of bread. Warm. Yielding. Alive. By day 4 or 5, you'll see white mycelial threads, that's fungal growth, and it's one of the most encouraging signs you can observe. Those threads are the primary agents breaking down lignin. Some people panic when they see white mold in their compost and turn the pile or add more water to suppress it. Don't. That white fuzz is your workforce. It means the system is working exactly as it should. Have you ever started a compost pile and then abandoned it because nothing seemed to be happening? I want you to tell me that in the comments, because I think it's one of the most common points of discouragement in home composting, and it's almost always caused by the absence of exactly the microbial density that this liquid provides from day 1. By the end of week 2, depending on leaf type and climate, you should have a material that looks and smells like partially finished compost. Dark, moist, with a rich earthy scent, that petrichor smell after rain, that deep forest floor smell. It won't be finished compost yet in the agronomic sense, but it will be biologically active and already beginning to return nutrients to any soil it contacts. Spread it thin, mix it with existing soil, or let it sit another week to fully mature. By month 2, if you've kept the pile moist and continued applying diluted FPJ every 7 to 10 days, what was once a 3-foot pile of dry autumn leaves will have reduced to perhaps 8 inches of dark, crumbly, sweet-smelling humus. That's roughly a 70 to 80% volume reduction, which mirrors the reduction you'd see in industrial composting operations that use mechanically aerated, temperature-controlled chambers. You've achieved industrial-scale biological efficiency using a fermented liquid you made from kitchen scraps and garden weeds. Think about what that means in terms of the emotional stakes I laid out at the beginning of this video. You are no longer waiting for the cycle to turn. You are no longer buying bags of compost from a supply chain that starts at an industrial facility somewhere and ends with a price tag. You are not dependent on a system that profits from your waiting. You close the loop. And every year it gets faster, because your soil, the living soil that this practice builds, becomes increasingly colonized by the organisms that make it work. The longer you do this, the more your garden begins to behave like that old-growth forest floor, predigesting, self-feeding, self-regenerating. There's something worth saying here that I don't think gets said enough in gardening content. The reason this knowledge is rare is not because it's difficult. It's not. The reason it's rare is because it doesn't require anything sold in a store. Traditional agricultural communities across Korea, Japan, Peru, and the Andean highlands didn't preserve these practices in expensive textbooks or certified training programs. They passed them hand to hand, voice to voice, season to season. When those communities were disrupted, by colonization, by forced agricultural modernization, by the post-war chemical revolution that swept through global farming with the promise of easier, faster, cheaper abundance, the knowledge broke. Not all at once. Not everywhere. But enough that most of us alive today never heard of FPJ, never heard of Biol, never heard of the idea that a fermented liquid could unlock a rate of decomposition that the composting industry's entire product line exists to simulate, imperfectly, at significant cost. You have this now. Share this video with someone who gardens, or someone who wants to start but thinks it's too slow, too complicated, too expensive to bother with. Because the barrier was never the skill. The barrier was the missing knowledge. And that missing knowledge is simply this: the soil wants to work. The organisms are already there, waiting. All you have to do is wake them up. Subscribe if you believe in unearthing what got buried, not because it was wrong, but because someone found it inconvenient. Next week, I'm going to show you the ancient buried structure that farmers across 3 continents used to store water underground for 6 months without any evaporation, any infrastructure, or any modern materials, and why civil engineers quietly rediscovered it 50 years ago and still haven't told the public about it. That one will change the way you look at drought. The leaves are waiting.